Hello everybody, and welcome to page 150 on the workbook. And on this page we are going to look at the least squares problem, the problem of taking a set of data points and trying to find the best fit line through those data points. Okay, so specifically, let's suppose that we have m points. We want to find the line that best fits those points. So in terms of a picture, we're kind of looking at this situation. We don't know what the equation of our line is yet, but we do know that it has the form of the equation of a line. So y equals ct plus d for some slope and vertical intercept c and d, which we have to figure out. Okay, and the idea is, since we're trying to find the best fit line, we're really trying to minimize the error between our line and these data points. So we're kind of interested in these vertical deviations between our data points and the line, and trying to get those deviations as small as possible if we add them all together. Okay, so to kind of get an expression for the error between the data points and the line, let's start with kind of a general point on the line ti, yi, and think about how we would measure the distance between that point and its counterpart that's on the line. Okay, so this point down here that I've labeled is going to have the same input coordinate ti. What would its output coordinate be? Well, if that point is on the line, we should be able to get its output coordinate by substituting ti into the ct plus d formula. So we'd get cti plus d. Okay, and so to measure the deviation between the two y values, that's what we want to get small. We would just take yi minus cti plus d, basically. Okay, I'm going to write that down up here. Okay, and it's customary to look at the squares of the errors, just so that all of these deviations are positive. Okay, and we need to do that, measure that deviation for every point on our line. So we're going to have a sum here going from 1 to m, one squared error for each point in our set. Okay, so this is going to be our expression for e, and our goal here is to get that error as small as possible. Okay, so we're trying to find c and d, our slope and vertical intercept, so that e, the error, is minimized. Okay, well, we can reformulate this problem in matrix form, which is going to allow us to use some of the tools that we developed earlier in the last section. Okay, so let's see if we can reformulate this problem in matrix form. Okay, to do this, we start by imagining, what if there were an exact solution to this problem? In other words, what if all of our data points really did lie on one line? Okay, well, that would mean that every yi that we have here would have to exactly match cti plus di. Okay, so for example, for the first data point, we would have to have y1 equals ct1 plus d. Then we'd move on to the second data point, we'd have to have y2 equals ct2 plus d, and so on, down our list of data points. Okay, and interestingly, we can reformulate that in terms of a matrix. I'm going to go ahead and write down the matrix form of this, and then we'll talk through it and convince ourselves that that really represents this same system. Okay, so here's our matrix. First column is just going to be the t's. Second column is going to be a bunch of 1s. We're going to multiply that by c and d, and I claim that that's going to be equal to all of our y's. Okay, and the claim that I'm making here is that these two things on the left and the right are the different ways of writing the same thing. Let's see if we can confirm that. So what if we multiplied the two matrices on the left-hand side? So we'd start by multiplying this row times this column. What do we get if we do that? ct1 plus d, that's what's sitting over here. And over on the right-hand side, we'd get y1, that's what's sitting over there. Okay, so ct1 plus d equals y1. That confirms the first equation. Then we'd move on. If you take T21 times CD, you get CT2 ct2 plus d, that's what we've got over here, equals y2, that's what we've got there. And you can confirm that if you go down the line, you're going to get exactly the same system of equations, so these really are equivalent. Okay, I'm going to give these pieces names here, so we'll call this matrix A, this vector x, and this vector y. Okay, and just to reemphasize, there probably isn't an exact solution to this problem. If there were, it would mean that all of our points lie on one line, and they probably don't. So we'll just point that out. There's probably no exact solution here. So what we're seeking is the best possible approximation, okay, the closest thing that we can get to a solution. That's going to minimize the error. Okay, so as we search for that best approximation, I want to start by noting a fact here. So you remember up at the beginning, we had a formula for the error that we'd like to minimize. It turns out that in terms of this new notation, this a, x, and y that we introduced, that same error winds up being the norm of the difference between y and ax squared. You could confirm this by direct calculation. Actually, taking ax, multiplying them together, we can see those two matrices up here, subtract it from y, take the norm squared the way we defined it, and you would discover that it gives you exactly the formula up here for e. Okay, it's just a different way of writing it down. Okay, and remind ourselves of our goal here again. We're looking for an x naught, a vector c and d, the slope and the vertical intercept, that minimizes the error. Okay, now here's where we can go back and use some of the things that we talked about in section 6.2. So I'd like to draw a picture representation of this. Okay, I think this is going to remind you of something that we did recently. Okay, so I'm going to imagine that we've got a subspace, W. That's going to be the range of L of A. Okay, A is just this matrix that we defined up here. Okay, so that would mean the set of all things that we can get out by multiplying A by something, the matrix A by something. Okay, so this vector y that we have up here, probably that vector y is not going to be in this plane, because if it were in this plane, it would mean that there's an exact solution to the problem above. Okay, so what we do is ask, what's the best possible approximation? We already talked about that situation when we did orthogonal projections. So the best possible approximation to a solution would be to project that y down onto this plane. We're going to get the orthogonal projection, which is going to have the form a times something. Okay, because of the way that we define w here, it's the range of L of A. Okay, and if all of that is true, then this vector that goes straight from the plane up to the tip of y, that has to be y minus ax naught, just by vector addition. Okay, and so the picture that we've drawn here exactly describes this orthogonal projection process that we talked about. And so, going back to theorem 6.6, that was the theorem that introduced orthogonal projections. We know that this vector right here has to be perpendicular to w. In other words, it's in w perp. Which is a very key fact here. That's going to lead us home to a solution. And so what we can say is that for any two-tuple of complex numbers, given that it's really true that y minus ax naught is in w perp, it has to be perpendicular to everything in w, which means if we take its inner product with ax, which is just an arbitrary vector that's in w, we have to get 0. Okay, and then, now that we've made this observation, we can use the adjoint theorem, which essentially lets us take this matrix A and move it over and turn it into a conjugate transpose. Okay, so we can rewrite this statement as follows. The inner product of x with a star times ax naught minus y. That has to be 0. I'm just going to mention that's the adjoint theorem. Okay, and then we notice that we kind of have an interesting equality that we're looking at here. So we've got an inner product that equals 0, and the thing I'd call your attention to is that x is arbitrary. And this inner product says that the inner product of that arbitrary x with this vector equals 0. There's a homework problem that you're going to do, or maybe already have done, that said if that happens, the only possibility is that this vector here has to be the 0 vector. Okay, so we can say then that a star times ax naught minus y has to be the 0 vector. Okay, and now we're going to do just some basic algebra and solve for x naught. So let's distribute the a star through. Okay, if we add a star y to both sides, we come up with a very interesting little equation. Okay, and I'd like to examine this in a little bit of detail and focus on that matrix. How big is that matrix that we just wrote down there? Okay, well, if we scroll up for a minute here, A is an m by 2 matrix. Okay, I'm just going to kind of sketch that here. So that means that a star is 2 by m. There's a transposed involved there. What would happen if you took a star times a, looked at the dimensions? You're going to get a 2 by 2 matrix here. Interesting. Okay, 2 by 2 is not very large. That's pretty computationally manageable. And if you do that same experiment and calculate the dimensions of a star and y, you're going to discover that this is a 2 by 1 vector. Okay, so this solution, what we're interested in this problem is figuring out x naught, because that's our best approximation, the one that minimizes the error. What we've demonstrated is that to find that, all we need to do is to solve a 2 by 2 system. All right, and so if we just scroll quickly to the next page here, Theorem 6.12, okay, I'm just gonna, sorry about that, I didn't mean to fill it in so quickly. We're gonna fill it in now together. Okay, so Theorem 6.12 just kind of summarizes all of this for us. Okay, so I'm not going to read this to you because it really just restates everything that we said and says that if you want to find the best approximation to this least squares problem, what you need to look at is this system of equations, the one that we just derived above. Okay, and a couple of notes here. The theorem provides a way of finding the best fit polynomial of degree n through m data points, and we just looked at the problem for n equals 2. That's the one that talks about a line, where we're looking for a line of best fit. All right, and so in the next video, we will actually do a specific example where we use this, okay, to find a line of best fit.